May 29, 1945. 29,000 feet above the Sea of Japan. Captain William Shomo throttles his P-51D Mustang to maximum continuous power and watches his airspeed indicator climb past 420 miles per hour. Below him, a formation of Japanese Zero fighters turns desperately to intercept, their Nakajima radial engines straining to match his altitude. They cannot. Their top speed at this height barely reaches 320 miles per hour. Their service ceiling ends 7,000 feet below Shomo's current position. The mathematics are brutal and absolute. Shomo's Mustang weighs 7,121 pounds, empty, carries 1,250 horsepower more than the Zeros, and flies 83 miles per hour faster at combat altitude. But the numbers that matter most are invisible to both pilots. Hidden in the crystalline structure of the aluminum alloy, forming his aircraft's wings and fuselage, lies a metallurgical advantage that Japanese engineers discovered too late to matter. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The P-51's airframe is constructed entirely from an American aluminum alloy designated 24S, 4.5% copper, 1.5% magnesium, 0.6% manganese, the rest aluminum and trace elements. This specific combination of metals, developed by Alcoa metallurgists in 1933, possesses tensile strength of 50,000 pounds per square inch, while maintaining the workability essential for mass production. The Zero fighters below Shomo carry their own advanced aluminum alloy, Extra Super Duralumin, developed by Sumitomo Metal's engineer Isamu Igarashi in 1936. Tensile strength 60,000 pounds per square inch, stronger than anything American metallurgists had achieved. But superior material strength means nothing when your aircraft cannot reach the altitude where battles are won. The Japanese had created the world's strongest aluminum alloy, then used it to build fighters that weighed 4,136 pounds empty, carried half the horsepower of American designs, and sacrificed everything for low-altitude maneuverability. Shomo rolls inverted and pulls through a split-S maneuver that generates forces exceeding 6 times the pull of gravity. The 24S aluminum in his wings flexes and absorbs the stress without permanent deformation. He accelerates downward past 500 miles per hour, faster than any Japanese aircraft can achieve even in a terminal dive. The Zeros scatter as his 650 caliber machine guns converge their fire through a single aiming point. The story of how American fighters came to dominate the Pacific skies begins not in combat, but in a Pittsburgh metallurgy laboratory, where a handful of civilian engineers challenged assumptions that had defined aluminum production since the First World War. Their work would transform aerial warfare through chemistry so precise it was measured in fractions of a sight inclines, 2%. But in 1931, when Alcoa's research division first proposed increasing the magnesium content in aircraft aluminum, the aviation industry dismissed the idea as unnecessarily complex. December 14, 1931. Alcoa Research Laboratories, New Kensington, Pennsylvania. The morning temperature hovers at 18 degrees Fahrenheit when metallurgist Robert Archer arrives at the facility where Alcoa conducts its most advanced alloy development. At 43, Archer has spent 2 decades working with aluminum, first at Aluminum Castings Company during the Great War, then at Alcoa, after the company acquired his employer in 1920. His current project addresses a problem that aircraft manufacturers across America have encountered with increasing frequency as engine power increases and flight speeds rise. The aluminum alloy, designated 17S, standard for aircraft construction since the mid-1920s, possesses design strength of 40,000 pounds per square inch, adequate for the biplanes and light aircraft of the previous decade. Insufficient for the high-performance designs now emerging from engineering departments at Boeing, Douglas, and Curtiss. Archer's laboratory notebook contains data from 6 months of systematic experimentation. Sample after sample of aluminum alloy with varying copper and magnesium content, each subjected to heat treatment at precisely controlled temperatures, then tested to destruction on universal testing machines that measure tensile strength, yield point, and elongation characteristics. The pattern emerging from his data contradicts conventional metallurgical wisdom. Standard 17S alloy contains 4% copper, 0.5% magnesium, and 0.5% manganese. The magnesium content, kept deliberately low to ensure consistent heat treatment results, limits the alloy's ultimate strength. But Archer's experiments show that increasing magnesium to 1.5% dramatically improves mechanical properties without sacrificing workability. The chemistry underlying this improvement involves phenomena occurring at the molecular level, invisible to any microscope available in 1931, but calculable through careful measurement of bulk properties. When aluminum alloy containing copper and magnesium undergoes solution heat treatment at 930 degrees Fahrenheit, the alloying elements dissolve into solid solution with the aluminum matrix. Rapid quenching in cold water freezes this supersaturated solution in place. Over subsequent days and weeks, copper and magnesium atoms precipitate from solution as submicroscopic particles of intermetallic compounds, aluminum-copper-magnesium phases with names like S' and θ'. These precipitate particles, each measuring only a few nanometers across, obstruct the movement of dislocations through the aluminum crystal lattice. This dislocation pinning dramatically increases the force required to deform the metal, raising tensile strength from 40,000 pounds per square inch to 50,000 without increasing weight or volume. But only if the magnesium content hits the precise level where solubility limits allow maximum precipitation density without creating coarse, brittle phases that weaken the material. Archer's task is to identify this optimal composition and prove it can be manufactured consistently at industrial scale. His preliminary results suggest 1.5% magnesium represents the sweet spot where strength, toughness, and formability converge. But laboratory samples measuring 6 inches by 12 inches prove nothing about production feasibility. Aircraft manufacturers require aluminum sheet in dimensions measured in feet, rolled to thicknesses between 32 thousandths and 125 thousandths of an inch, with mechanical properties that remain consistent across entire production runs of thousands of panels. The telephone call that validates Archer's research arrives on January 23, 1933, from Donald Douglas at Douglas Aircraft Company in Santa Monica, California. Douglas is designing a new twin-engine transport aircraft intended to revolutionize commercial aviation. The DC-1, and its production derivative, the DC-2, will carry passengers at speeds approaching 200 miles per hour across ranges exceeding 1,000 miles. But achieving this performance requires structural weight reduction that standard 17S aluminum cannot provide. Douglas has reviewed Archer's preliminary data on the high magnesium alloy. His structural engineers calculate that substituting the new material for 17S in wing spars, fuselage stringers, and skin panels will save 400 pounds of structural weight. 400 pounds that can be converted to additional fuel capacity, increased payload, or improved performance margins. The contract Douglas offers Alcoa specifies delivery of 20,000 pounds of the new alloy in sheet form, with guaranteed minimum tensile strength of 50,000 pounds per square inch and elongation of at least 10%. Delivery deadline is 6 months. This represents the largest single order for experimental aluminum alloy in aviation history. It also represents a manufacturing challenge that will require Alcoa to scale laboratory processes to industrial production without losing the precise metallurgical control that creates the alloy's superior properties. Archer convenes his development team on January 25th in the New Kensington laboratory. Present are plant metallurgists from Alcoa's rolling mills in Massena, New York, and Cleveland, Ohio, representatives from the Quality Control Department who will develop testing protocols for production material, and technical sales engineers who will work directly with Douglas Aircraft to ensure the alloy meets aircraft construction requirements. The alloy receives its official Alcoa designation, 24S, indicating it is the 24th sheet alloy in the company's development sequence. The S suffix denotes wrought condition, distinguishing it from casting alloys that use different designations. The complete specification defines composition within narrow tolerances, copper content between 3.8 and 4.9%, magnesium between 1.2 and 1.8%, manganese between 0.3 and 0.9%, silicon, iron, and other impurities held below strict maximum limits to prevent formation of coarse intermetallic particles that would reduce ductility and fatigue resistance. Manufacturing 24S alloy requires modifications to existing production procedures at every stage, from casting to final heat treatment. The process begins at Alcoa's ingot casting facilities, where molten aluminum containing the specified alloying elements is solidified into large rectangular blocks weighing several thousand pounds. The direct chill casting process, invented by Alcoa engineer William Shomo earlier in the decade, controls solidification by continuously withdrawing the ingot from the mold while water sprays cool the solidifying metal. Precise control of cooling rate during casting is essential because rapid cooling produces fine-grained microstructure with uniform distribution of alloying elements. Too slow, and copper-rich phases segregate to grain boundaries, creating zones of weakness where cracks initiate during subsequent processing. The metallurgists establish cooling parameters through systematic trials, measuring grain size and phase distribution in cast ingots until they achieve the uniformity required for consistent rolled sheet properties. Hot rolling reduces the cast ingot from 6 inches thick to 1 inch through a series of passes between massive steel rolls heated to 700 degrees Fahrenheit. At this temperature, the aluminum alloy flows plastically under pressure without FIVOs, cracking, while mechanical working breaks up the cast microstructure and aligns the grain structure in the rolling direction. Each rolling pass reduces thickness by 10 to 20%, requiring multiple heating cycles and progressive roll adjustments to achieve final gauge. Cold rolling brings the material from 1 inch down to final sheet thickness at ambient temperature. This work hardens the aluminum, increasing strength but reducing ductility. The metallurgists must balance the degree of cold work against the final heat treatment to achieve specified properties. Too much cold reduction, and the material becomes too hard to form into aircraft components. Too little, and strength falls below requirements. Solution heat treatment at 930 degrees Fahrenheit dissolves the copper and magnesium into solid solution. The sheet material enters continuous furnaces, where temperature is maintained within plus or minus 5 degrees across the entire heating zone. Dwell time of 30 minutes ensures complete dissolution. Any variation in temperature or time produces inconsistent properties that aircraft manufacturers cannot tolerate. Quenching immediately after solution treatment is the most critical step. The heated sheet exits the furnace and plunges into cold water within 15 seconds. This rapid cooling freezes the supersaturated solid solution before alloying elements can precipitate as coarse particles. If quenching delay exceeds 30 seconds, or if water temperature rises above 80 degrees Fahrenheit, precipitation begins prematurely and final strength drops by 10% or more. Natural aging occurs at room temperature over the next 4 to 5 days, as copper and magnesium atoms migrate through the aluminum lattice and precipitate as submicroscopic coherent particles. This precipitation hardening increases tensile strength from 35,000 pounds per square inch immediately after quenching to 50,000 after complete aging. The process is spontaneous and does not require external heating, a phenomenon discovered by German metallurgist Alfred Wilm in 1906, but not fully understood until Paul Merica's research at the National Bureau of Standards in the 1920s. The first production shipment of 24S sheet arrives at Douglas Aircraft in Santa Monica on June 7, 1933. Receiving inspection confirms the material meets all specifications. Tensile strength 52,000 pounds per square inch. Yield strength 40,000 pounds per square inch. Elongation 12%. The quality control data shows remarkably consistent properties across the entire shipment, validating Alcoa's production process scale-up. Douglas structural engineers immediately begin cutting and forming the 24S sheet into wing ribs, spars, and skin panels for the DC-1 prototype. The material machines cleanly with standard tools, Bending and forming operations proceed without cracking. Riveting produces sound joints without material tearing around fastener holes. Every manufacturing characteristic matches or exceeds the properties of standard 17S alloy, while delivering 25% higher strength. The weight savings are substantial and immediately apparent. The DC-1's wing structure, fabricated from 24S instead of 17S, weighs 380 pounds less than equivalent structure in heavier alloy. Fuselage skin and stringers save another 90 pounds. The total reduction of 470 pounds allows Douglas engineers to increase fuel capacity by 70 gallons without exceeding design weight limits. The DC-1 prototype makes its first flight on July 1, 1933, from Clover Field in Santa Monica. Test pilot Carl Cover reports excellent handling characteristics and performance that exceeds projections. Maximum speed 196 miles per hour at cruise altitude. Service ceiling 21,000 feet. Range 1,000 miles with full payload. These numbers represent dramatic improvements over existing transport aircraft. Improvements made possible by the structural efficiency of 24S aluminum alloy. Word spreads rapidly through the aviation industry. Boeing, Lockheed, Curtiss, and Northrop all place orders for 24S alloy. By 1937, every major American aircraft manufacturer has standardized on the material for primary structural components. Nearly all of the 300,000 aircraft built in the United States during the Second World War incorporate 24S alloy in their airframes. But in 1937, as American metallurgists celebrate their achievement, Japanese naval engineers issue a specification that will challenge everything American designers believe about aluminum alloy development. The Imperial Japanese Navy demands an aluminum alloy with tensile strength exceeding 60,000 pounds per square inch, higher than any material in production anywhere in the world. Sumitomo Metals assigns the project to their most capable metallurgist, a young engineer named Isamu Igarashi, who has spent 5 years studying aluminum-zinc-magnesium alloys. Igarashi's approach differs fundamentally from the American path. While Alcoa focused on aluminum-copper-magnesium alloys optimized for aircraft production, Igarashi explores aluminum-zinc-magnesium compositions where zinc content reaches 7% and magnesium climbs above 2%. These high-solute alloys exhibit extraordinary strength through dense precipitation of multiple intermetallic phases, but they also present severe manufacturing challenges, including stress corrosion, cracking susceptibility, and weld crack sensitivity. By 1936, Igarashi succeeds in developing what the Japanese designate extra super duralumin, or ESD. Tensile strength 62,000 pounds per square inch, exceeding the Navy's requirement. The alloy receives immediate application in the Mitsubishi, a 6M0 fighter, specifically in the main wing spar flanges where bending loads reach maximum values during combat maneuvering. American intelligence does not learn about ESD until 1942, when Navy personnel recover an intact Zero from the Aleutian Islands. Metallurgical analysis of the wing structure reveals aluminum alloy with properties superior to any American material. The discovery triggers urgent programs at Alcoa and rival Reynolds Metals to develop equivalent high-strength alloys. The result is aluminum alloy 7075, containing 5.6% zinc, 2.5% magnesium, and 1.6% copper. Tensile strength 78,000 pounds per square inch after artificial aging heat treatment. The alloy enters production in late 1943 and finds immediate application in B-29 Superfortress wing structures, where high strength enables construction of the massive wing panels required for high-altitude pressurized flight. But 7075 arrives too late to affect P-51 Mustang production. Every Mustang built during the war uses 24S alloy, the same material that Douglas pioneered in the DC-1 a decade earlier. The metallurgical advantage American fighters possess over their Japanese opponents comes not from superior alloy strength, but from superior aircraft design that exploits available materials to achieve decisive performance superiority. August 17th, 1943. The Schweinfurt-Regensburg mission. 230 B-17. Flying fortresses penetrate deep into southern Germany to attack ball-bearing factories essential to German war production. They fly without adequate fighter escort. The P-47 Thunderbolts, assigned to protect them, possess combat radius of only 475 miles, forcing them to turn back 100 miles short of the target area. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. 60 bombers fail to return. 599 airmen killed, wounded, or captured. The disaster validates everything critics of daylight strategic bombing have argued. Unescorted heavy bombers cannot survive against determined fighter opposition. German interceptors possess overwhelming tactical advantages when they can engage bombers without interference from Allied fighters. The entire strategic bombing campaign faces potential cancellation unless Allied fighters can be extended to escort bombers throughout their mission radius. The solution exists but remains incomplete. North American aviation has delivered 300 P-51B Mustangs to the 8th Air Force by mid-August. These aircraft possess the range to escort bombers to any target in Germany, but converting fighter groups from P-47 seconds to P-51 seconds requires months of pilot transition training, maintenance crew familiarization, and logistics system modifications. The Mustang will not deploy in significant numbers until late autumn. Meanwhile, Alcoa's production facilities operate at maximum capacity to supply 24S aluminum sheet for Mustang production at North American's Inglewood, California factory and new facility in Dallas, Texas. The metallurgical challenges Robert Archer solved in laboratory samples a decade earlier now replicate across industrial operations, measuring output in millions of pounds per month. Quality control becomes critical as production scales geometrically. Every sheet of 24S aluminum leaving Alcoa's rolling mills must meet specifications within narrow tolerances. Tensile strength between 50,000 and 57,000 pounds per square inch. Yield strength minimum 40,000 pounds per square inch. Elongation minimum 10% in 2-inch gauge length. Any material falling outside these limits gets rejected and reprocessed, causing production delays that cascade through the entire aircraft manufacturing system. The testing protocols Alcoa develops to ensure consistent quality establish standards that persist into modern aerospace production. Each production lot undergoes statistical sampling, where representative specimens are machined into standard tensile test bars. Universal testing machines apply steadily increasing loads until the specimens fracture, recording stress-strain curves that reveal material properties. Metallographic examination of polished and etched samples confirms proper grain structure and precipitate distribution. Hardness testing on production sheets provides rapid quality verification before material ships to aircraft manufacturers. These quality assurance procedures require investment in laboratory equipment and trained personnel. Alcoa establishes dedicated quality control laboratories at every facility producing aircraft alloy. The laboratories employ metallurgists, technicians, and inspectors whose sole responsibility is verifying that every pound of aluminum leaving the plant meets specification requirements. The cost is substantial but essential. A single batch of off-specification material incorporated into aircraft structures could result in fleet-wide grounding while engineers determine structural safety margins. North American Aviation implements parallel quality control at their manufacturing facilities. Incoming aluminum sheet undergoes receiving inspection before acceptance. Random samples from each shipment get tested to confirm mechanical properties match mill certifications. Any discrepancy triggers investigation to identify whether variation stems from material production or testing procedure differences. The rigorous verification protocols ensure that every Mustang airframe contains aluminum alloy with properties falling within the narrow window where structural efficiency and reliability intersect. The manufacturing process that transforms aluminum sheet into Mustang components demonstrates why optimizing alloy formability proved as important as maximizing strength. Wing skin panels require stretching over compound curved molds to achieve the precise aerodynamic contours that minimize drag. Fuselage sections demand deep drawing operations that form flat sheet into complex three-dimensional shapes. Structural members like wing ribs and bulkheads undergo press brake forming to create the angles and flanges that distribute loads through the airframe. Each forming operation stresses the aluminum beyond its elastic limit, permanently deforming the metal into the desired shape. The material must possess sufficient ductility to stretch without tearing, yet enough strength after forming to carry flight loads. The 1.5% magnesium content in 24S aluminum provides precisely this balance. Lower magnesium alloys like 17S lack adequate strength. Higher magnesium compositions tend to crack during severe forming operations. The rivet holes drilled through every joint present another critical design consideration. Each Mustang airframe contains approximately 60,000 rivets, securing overlapping aluminum panels and attaching stringers to skin. The drilling process creates stress concentrations at every hole. Under cyclic loading during flight, these stress concentrations can initiate fatigue cracks that propagate through the structure. The aluminum alloy must possess sufficient fracture toughness to resist crack growth while maintaining high strength in the rivet-bearing areas. 24S aluminum in the T3 temper condition, achieved through controlled natural aging after solution heat treatment and cold working, delivers optimal fatigue resistance for airframe applications. The fine precipitate structure strengthens the aluminum matrix while maintaining grain boundaries that resist crack propagation. Flight testing validates the design under realistic conditions where wings flex thousands of cycles as the aircraft encounters turbulence and executes maneuvers. No widespread fatigue failures emerge during the war years, despite operational stresses that frequently exceed design limits. The manufacturing scale North American aviation achieves demonstrates American and industrial capacity at its peak. The Inglewood factory employs 30,000 workers operating 3 shifts around the clock. Raw aluminum sheet enters at one end of the mile-long assembly facility. Completed Mustangs emerge from the other end at a rate exceeding 15 aircraft per day during peak production periods. The Dallas factory, built specifically for Mustang production, adds similar capacity beginning in 1943. This production rate requires aluminum supply measured in thousands of tons monthly. Alcoa expands its 24S manufacturing capacity through government-financed construction of new rolling mills and heat treatment facilities. Reynolds Metals, Alcoa's primary competitor, also produces aluminum alloy to military specifications under licensing agreements that share Alcoa's proprietary heat treatment procedures. The combined output from American aluminum producers reaches levels that German and Japanese industry cannot approach even before Allied bombing disrupts Axis manufacturing. The strategic implications become clear as Mustang deployments accelerate through late 1943 and early 1944. Every fighter group conversion from short-range P-47 seconds to long-range P-51 seconds extends the protective radius around bomber formations. German interceptors face growing difficulty finding opportunities to attack unescorted bombers. The kill ratios that favored German fighters during unescorted missions reverse dramatically once Mustangs arrive in theater with sufficient numbers to maintain continuous coverage. Lieutenant Colonel James Howard demonstrates the tactical transformation during a mission to Oschersleben on January 11, 1944. Flying as lone escort when his squadron becomes separated from the bomber stream, Howard encounters more than 30 German fighters attacking B-17 seconds. Rather than withdrawing against overwhelming numerical odds, he exploits his Mustang's performance advantages to disrupt enemy formation. Superior speed allows him to close rapidly on attacking fighters. Greater altitude capability lets him maintain energy advantage throughout the engagement. Extended endurance provides combat persistence that German pilots cannot match. Over 30 minutes of continuous combat, Howard shoots down multiple German aircraft while driving others away from the bombers. His fuel gauges show reserves remaining when the engagement ends, demonstrating the operational flexibility that long range provides. The bomber crews he protected submit reports crediting his intervention with saving their aircraft from certain destruction. Howard receives the Medal of Honor for his actions, but the true significance lies in demonstrating that individual Mustang pilots with superior aircraft can dominate numerically superior opposition. The aluminum alloy enabling this tactical revolution receives no medals or public recognition. The metallurgists who developed it work in anonymity at the industrial facilities far from combat zones. The production workers who manufacture it operate rolling mills and heat treatment furnaces in 3-shift rotations that receive no newspaper coverage. The quality control inspectors who verify every shipment perform essential but unglamorous tasks that merit no public celebration. Yet their collective contribution matters as much as the pilots who flew combat missions and the engineers who designed the airframe. Without 24S aluminum alloy available in adequate quantities with consistent quality, the Mustang exists only as paper design, regardless of its aerodynamic excellence or engine performance. The material forms the literal foundation on which all other capabilities depend. Its strength enables the thin section design that minimizes weight. Its formability permits the compound curves that reduce drag. Its fatigue resistance ensures structural integrity through thousands of flight hours under combat conditions. The Japanese recognition of their material advantage arrives too late to influence strategic outcomes. When American forces recover the intact Zero from the Aleutians in mid-1942 and discover the extra superduralumin alloy, Japanese industry is already straining under resource limitations that prevent expanding ESD production. The complex heat treatment procedures required for the high zinc-magnesium alloy demand tight process control that becomes impossible to maintain as American bombing disrupts electrical power generation and industrial infrastructure. By 1944, Japanese aircraft production increasingly relies on substitute materials as aluminum supplies dwindle. Some Zero fighters emerge from factories with wooden components replacing aluminum structures. Others incorporate salvaged aluminum from wrecked aircraft, material whose properties are unknown and potentially dangerous in structural applications. The theoretical advantages of extra superduralumin become irrelevant. When aircraft cannot be built in sufficient numbers with consistent quality, American production faces no such constraints. Aluminum supply expands continuously throughout the war, as government investment creates new smelting capacity and recycling programs, recover material from training aircraft and combat losses. The 24S alloy formulation remains unchanged from 1933 specification through war's end, providing manufacturing consistency that simplifies production and ensures reliable performance. North American aviation never needs to redesign Mustang structures to accommodate material property variations because Alcoa delivers aluminum that meets specifications month after month and year after year. The contrast between American industrial capacity and Japanese limitations appears starkly in production statistics. American factories build 15,000 P-51 Mustangs between 1943 and 1945. Japanese industry produces 10,930 Zeros over the entire war, from 1940 through 1945. Despite the Zero's earlier start date and longer production run, the production rate differential, approximately 2-to-1 favoring American manufacturing, reflects fundamental differences in industrial organization and resource availability that no amount of materials science innovation could overcome. The metallurgical lesson reinforces strategic realities. Superior materials cannot compensate for insufficient production capacity. Advanced alloy development matters little when industry lacks resources to manufacture components at scale. The best material is not the strongest or lightest, but the one that balances performance against manufacturability and availability. Adequate properties achieved consistently across massive production volumes defeat superior properties delivered in limited quantities with uncertain quality. These principles, validated through the crucible of global conflict, guide materials selection decisions in applications extending far beyond aviation. Every engineered product requiring structural materials faces similar trade-offs between performance and practicality. The optimal solution rarely maximizes any single property, instead balancing competing requirements to achieve the best overall system performance within real-world constraints. The engineers who developed 24S aluminum alloy understood these trade-offs intuitively through years of experience working with practical manufacturing challenges. They specified composition limits that provided adequate strength while maintaining excellent formability. They established heat treatment procedures that achieved consistent properties without requiring exotic equipment or extreme process control. They created an alloy that could be produced in the quantities required, worked into the shapes necessary, and relied upon to perform as specified under the most demanding conditions imaginable. Their achievement receives validation. Every time an aircraft carrying aluminum alloy descended from their original formula completes a mission successfully. The validation continues into the present day as 2024 aluminum, essentially unchanged from the 1933 24S specification, remains standard material for aircraft structure, requiring high strength-to-weight ratios combined with excellent fatigue resistance and damage tolerance. March 8, 1944. RAF Debden Airfield, Essex, England. Captain Don Gentile walks his pre-flight inspection around P-51B, serial number 4-3-6-6-7-3, call sign Shangri-La. The aircraft weighs 10,700 pounds, fully loaded with fuel, ammunition, and external drop tanks. In 20 minutes, Gentile will lead his squadron to escort Boeing B-17 bombers attacking Berlin, penetrating 350 miles into German airspace, where no Allied fighter has previously operated. The mission profile requires capabilities that would have been impossible 3 years earlier. Combat radius of 475 miles, carrying two 108-gallon drop tanks. Sustained cruise speed of 360 miles per hour at 25,000 feet altitude. Maximum combat speed exceeding 430 miles per hour. Service ceiling 41,900 feet, high enough to intercept any German aircraft in production. These performance numbers derive directly from the structural efficiency that 24S aluminum alloy enables. The Mustang's wings carry internal fuel cells holding 184 gallons in space, created by thin aluminum sheet formed into complex aerodynamic shapes. Each wing skin panel measures 40 thousandths of an inch thick, supported by stamped ribs and extruded spars that distribute flight loads through the structure. The material's 50,000 pound per square inch tensile strength allows these thin sections to withstand the bending moments generated during 6G combat maneuvers, while weighing only 1,100 pounds for the complete wing structure. German fighters defending Berlin that day encounter tactical realities they have never faced in previous combats with Allied escort fighters. The Messerschmitt Bf-109G pilots, accustomed to engaging shorter-range P-47 Thunderbolts and P-38 Lightnings that must turn back before reaching the target area, discover American fighters over Berlin with full combat capability. The Mustangs arrive with sufficient fuel reserves to engage in extended air combat, then escort the bombers home. Major Gunther Rahl, commanding Jagdgeschwader 11 inches defense of the Reich, files a combat report that evening, describing the transformation in Allied fighter capability. American escort fighters now possess range exceeding German interceptor aircraft. They maintain altitude and speed advantages throughout the engagement. Most significantly, they carry sufficient fuel to dictate the terms of combat, attacking when tactical conditions favor Allied pilots and disengaging when outnumbered. The structural elements enabling this capability remain invisible to German intelligence analysts studying captured Mustang wreckage. They can measure wing dimensions and calculate internal volume. They can examine fastener patterns and fabrication techniques. They can identify the aluminum alloy through chemical analysis. But they cannot replicate the integrated design that exploits 24S properties to achieve optimal structural efficiency. North American Aviation's chief designer Edgar Schmude had optimized the Mustang airframe around 24S material characteristics from the project's inception in 1940. He specified sheet thicknesses that balanced strength requirements against weight penalties. He positioned structural reinforcements where stress analysis indicated maximum loads. He designed wing skins with sufficient stiffness to maintain laminar flow across the pillars. Airfoil surface, reducing drag and increasing top speed. The result is an aircraft that carries more fuel per pound of structural weight than any fighter in production. The P-51D variant, with enlarged fuselage fuel tank capacity, holds 269 gallons internally, plus provision for 2 external drop tanks carrying 110 gallons each. Total fuel, load 489 gallons, weighing 2,934 pounds. This massive fuel capacity, combined with the efficiency of the Packard-built Merlin engine, delivers combat radius exceeding 550 miles. Japanese pilots encountering Mustangs over the home islands in early 1945 face similar tactical disadvantages. The Zeros defending Tokyo possess superior low-speed maneuverability, legacy of Jiro Horikoshi's design philosophy, emphasizing turn performance above all other characteristics. But maneuverability means nothing when American pilots refuse to engage in turning combat. The standard engagement technique American pilots employ against Zeros exploits every performance advantage the Mustang possesses. Approach from high altitude with speed exceeding 400 miles per hour. Attack in a slashing dive, bringing 650 caliber machine guns to bear for a 2-second firing pass. Continue the dive to build speed above 500 miles per hour, far beyond anything the Zero can match. Climb back to altitude using superior power-to-weight ratio. Repeat until enemy formation breaks or ammunition exhausts. Zero pilots attempting to counter these tactics discover their aircraft cannot climb fast enough to intercept diving Mustangs, cannot dive fast enough to escape climbing Mustangs, and cannot sustain high-speed flight long enough to force extended combat. The extra super duralumin alloy forming their wing spars possesses superior tensile strength compared to American 24S, but this material advantage delivers no tactical benefit when the aircraft carrying it cannot reach the altitude where battles occur. The fundamental truth American engineers understood and Japanese designers missed is that aircraft performance derives from integrated systems optimization, not component-level material superiority. A zero-wing spar made from 62,000 pound per square inch aluminum weighs slightly less than an equivalent spar in 50,000 pound per square inch material, but the weight savings amount to perhaps 20 pounds across the entire airframe. These 20 pounds matter far less than the additional 1,000 horsepower the Mustang's Merlin engine produces, or the 400 mile/hour cruise speed enabled by low-drag aerodynamics, or the 5,500 feet of additional service ceiling provided by effective supercharging. American victory in the air war over both Europe and the Pacific ultimately rests on industrial and tactical integration rather than metallurgical supremacy. Alcoa's 24S alloy provided adequate strength for airframe construction while maintaining the formability and weldability essential for mass production. American aircraft factories delivered 15,000 P-51 Mustangs between 1943 and 1945, each built to consistent quality standards using proven manufacturing techniques scaled for high-volume production. Japanese industry, despite developing superior aluminum alloy, never achieved comparable production efficiency. Total Zero production reached 10,930 aircraft over the entire war, built in factories increasingly disrupted by American bombing and resource shortages. The advanced ESD alloy required more careful processing than standard materials, compounding production challenges as Japan's industrial infrastructure deteriorated. The numbers that matter most appear in post-war statistical analysis compiled by the United States Strategic Bombing Survey. American fighters destroyed 4,950 enemy aircraft in aerial combat. P-51 Mustangs accounted for roughly half these victories despite entering service relatively late in the war. The kill-to-loss ratio for Mustangs exceeded 3-1 against German opposition and reached higher levels against Japanese aircraft. These combat results validate the engineering philosophy that guided American aluminum alloy development. Robert Archer and his colleagues at Alcoa designed 24S not to achieve maximum theoretical strength, but to deliver optimal combination of properties for aircraft production. The alloy's 50,000 pound per square inch tensile strength provided adequate structural capability, while maintaining low cost, high availability, and consistent quality across massive production volumes. The metallurgical lesson transcends wartime applications. Modern aluminum alloys trace their lineage directly to the 24S formula developed in 1933. The current designation, 2000, 24 aluminum alloy uses nearly identical composition, 4.4% copper, 1.5% magnesium, 0.6% manganese. Tensile strength specifications remain essentially unchanged at 64,000 pounds per square inch in T3 temper. Aircraft manufacturers in the 21st century still specify 2024 aluminum for wing skins, fuselage stringers, and structural components requiring high strength-to-weight ratios. The superior Japanese ESD alloy eventually evolved into the 7075 aluminum alloy that American manufacturers adopted in 1943. This material family, with zinc as the primary alloying element, now dominates applications requiring maximum strength. Modern 7075 aluminum develops tensile strength exceeding 83,000 pounds per square inch, making it standard for aerospace components operating under extreme stress. But 2024 aluminum persists in applications where strength combines with formability and fatigue. Resistance. Characteristics Archer optimized 9 decades ago. The human cost of material science decisions made in Pittsburgh and Tokyo laboratories appears in casualty statistics from both theaters. American pilots flying Mustangs with 24S aluminum airframes enjoyed survival rates significantly higher than contemporaries in earlier aircraft types. The structural strength enabled combat damage tolerance that allowed pilots to return safely despite battle damage that would have destroyed aircraft built from weaker materials. Japanese pilots flying Zeros with ESD aluminum spars faced increasing casualties as the war progressed, and American fighter performance improved. The Zero's light structure, optimized for maneuverability at the expense of protection and speed, proved fatally vulnerable to the heavy machine gun armament American fighters carried. The superior spar alloy could not compensate for fundamental design choices that sacrificed pilot survival for aerobatic performance. The irony, visible only in historical retrospect, is that both nations made rational engineering decisions based on their strategic circumstances and design philosophies. American engineers, working in an industrial system with massive productive capacity and abundant resources, optimized for manufacturing efficiency and integrated system performance. Japanese engineers, constrained by limited industrial capacity and resource shortages, maximized individual component performance through advanced materials development. American strategy proved correct for total war, requiring mass production and sustained operations across global distances. Japanese strategy might have succeeded in a limited conflict decided by quick victories achieved through qualitative superiority. But the Second World War became the former type of conflict rather than the latter, and industrial capacity ultimately mattered more than materials science sophistication. Captain William Shomo, climbing away from the engagement over the Sea of Japan on May 29, 1945, cannot know these strategic calculations. He knows only that his Mustang's performance envelope exceeds every Japanese aircraft in operational service. He knows the aluminum alloy forming his wings and fuselage has performed flawlessly through hundreds of flight hours and dozens of combat missions. He knows he will return safely to base, while enemy pilots below struggle to reach the altitude where his aircraft operates with complete tactical freedom. The metallurgists who developed 24S aluminum in Pittsburgh laboratories 13 years earlier never flew in combat. Robert Archer spent the war years expanding Alcoa's production capacity to meet military demand, supervising the manufacture of millions of pounds of aircraft alloy. He died in 1949, recognized within the metallurgical community, but unknown to the general public, whose survival his work ensured. The aluminum alloy he developed outlived him by decades and continues serving in aircraft construction into the 21st century. Every commercial airliner flying today incorporates 2024 aluminum alloy in structural components, where his original formula still provides optimal properties. Every military fighter carries materials descended directly from his 1933 innovation. The engineering principles he established, balancing strength against manufacturability and cost, guide materials selection decisions in applications far beyond aviation. The P-51 Mustang that dominated the skies over Germany and Japan carried no revolutionary materials technology. Its aluminum alloy was standard production material available to any aircraft manufacturer worldwide. Its structural design exploited well-understood principles of stress analysis and aerodynamic optimization. Its manufacturing employed conventional techniques scaled to high-volume production, but the integration of these conventional elements, guided by engineers who understood that adequate performance achieved quickly and cheaply defeats superior performance delivered slowly and expensively, produced the most effective fighter aircraft of the Second World War. The lesson extends far beyond aluminum alloys and aircraft design. In any contest between adversaries with roughly equivalent technical sophistication, victory goes to whichever side better integrates available technology into practical systems that can be produced in quantity and sustained over time. The Germans developed jet fighters with performance exceeding any Allied piston engine aircraft. The Messerschmitt Me-262 could outrun, outclimb, and outdive every American fighter in service. But Germany produced only 1,400 Me-262 seconds before industrial collapse ended production. The United States built 15,000 P-51 Mustangs, each carrying 24S aluminum alloy developed 12 years before the war began and manufactured in quantities that German industry could never match. The Japanese developed extra superduralumin, with strength exceeding American materials by 24%. But they built 10,900 Zeros against 15,000 Mustangs, and the stronger alloy provided no tactical advantage when the aircraft carrying it could not compete in the performance parameters that decided combat outcomes. The arithmetic of industrial warfare favored the side that optimized entire systems rather than maximizing individual components. The aluminum alloy that mattered most was not the strongest or lightest or most advanced. It was the alloy that could be produced in the quantities required, worked in the shapes necessary, and integrated into aircraft designs that exploited every performance advantage available from existing technology. Robert Archer understood this when he specified 1.5% magnesium in 24S aluminum alloy, not 1.8%. Which might have provided slightly higher strength at the cost of manufacturing difficulties. Not 1.2%, which would have simplified heat treatment while sacrificing strength. Precisely 1.5%, the composition that balanced all competing requirements to deliver adequate performance at achievable cost in sustainable volumes. This metallurgical calculation, made in a Pittsburgh laboratory in 1933, influenced the outcome of history's largest conflict. It enabled aircraft that dominated the skies over Europe and the Pacific. It saved thousands of Allied pilots whose structural protection depended on strong, reliable airframes. It contributed to strategic victory through unglamorous optimization of manufacturability over maximum performance. The legacy appears in every modern aluminum alloy specification, where composition limits define narrow windows, achieving optimal property combinations. It persists in engineering philosophy, emphasizing integrated system performance over component-level excellence. It validates the principle that adequate solutions implemented broadly defeat superior solutions implemented narrowly, and it demonstrates that sometimes the most revolutionary technological achievement is recognizing that revolution is unnecessary, that incremental improvement of existing materials, guided by clear understanding of practical requirements, delivers better results than pursuit of theoretical maximum performance. That the best answer to an engineering challenge is often the simplest solution that works reliably at scale. The P-51 Mustang, flying 430 miles per hour at 40,000 feet, carried no secret weapons, just conventional aluminum alloy, well understood and carefully applied, just proven engineering principles, methodically executed, just industrial capacity, efficiently employed. And with these conventional elements, American pilots flying American fighters, built from American aluminum, achieved complete air superiority over opponents whose materials science was in some cases technically superior. The alloy designated 24S developed by civilian metallurgists working for a Pittsburgh aluminum company, gave American fighters the structural foundation for dominance in the sky. Not through revolutionary breakthrough, but through careful optimization of composition and properties to meet practical requirements. Not through maximum strength, but through adequate strength, achieved consistently in massive production volumes. Not through exotic materials, but through incremental improvement of conventional alloys to deliver decisive performance advantages when multiplied across thousands of aircraft fighting a global war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.